All right, welcome to the notes on reflection and refraction. These are going to be done in two parts. This is part one. When waves interact with matter, they can be reflected, transmitted, or a combination of both. Waves that are transmitted can be refracted. Light doesn't travel through a mirror, but is returned to the mirror's surface. These waves are reflected. When a wave strikes the surface of a medium at an angle, their directions change. These waves are refracted. Usually waves are partly reflected and partly refracted when they fall in a transparent medium. When a wave reaches a boundary between two media, usually some or all of the wave bounces back into the first medium. The return of a wave back to its original medium is called reflection. Fasten a spring to a wall and send a pulse along the spring's length. The wall is a very rigid medium compared to the spring, so all the wave energy is reflected back along the spring. Waves that travel along the spring are almost totally reflected at the wall. So as they move down this direction, they hit the wall and it travels back the other direction. This is reflection. If the wall was replaced with a less rigid medium, such as a heavy spring, some energy is transmitted into the new medium. Some of the wave is still reflected. The incoming wave is partially reflected. So as this wave right here travels down, it hits the other wave, and if you look, some of the wave travels into here, and the part of it is reflected back. A metal surface is rigid to the light waves that shine upon it. Light energy does not propagate into the metal, but instead is returned into a reflected wave. This is why metals such as silver and aluminum are so shiny. They reflect almost all the frequencies of visible light. Materials such as glass and water are not as rigid to light waves. When light shines perpendicularly on the surface of still water, about 2% of its energy is reflected, and the rest is transmitted. When light strikes glass perpendicularly, about 4% of its energy is reflected. Except for slight losses, the rest is transmitted. What happens when a wave reaches a boundary between two media? The law of reflection states that the angle of incident and the angle of reflection are equal to each other. In one dimension, reflected waves simply travel back into the direction from which they came. In two dimensions, the situation is a little different. The direction of incident and reflected waves is described by straight line rays. Incident rays and reflected rays make equal angles with a line perpendicular to the surface called the normal. The angle between the incident ray and the normal is called the angle of incident. The angle between the reflected ray and the normal is called the angle of reflection. The angle of incident will equal the angle of reflection. As the light ray comes in and then bounces off, it makes a perpendicular line right here with what is called the normal. That's the normal. So in the angle here, which is the incident angle, and the angle here is the angle of reflection, and both those angles are equal to each other. The law of reflection states that the angle of incident and the angle of reflection are equal to each other. The incident ray, the normal, and the reflected ray all lie in the same plane. The law of reflection applies to both partially reflected and totally reflected. This is important. All of the rays will follow this. You look at your blue shirt in a mirror. What is the color of the image? What does this tell you about the frequencies of light upon a mirror compared to the frequencies of light after it is reflected? The color of the image will be the same as the color of the object because the frequencies of light is not changed by reflection. Everything stays the same. What is the law of reflection? Mirrors produce only virtual images. If a candle flame is placed in front of a plain flat mirror, rays of light from the candle are reflected from the mirror in all directions. Each of the infinite number of rays obeys the laws of reflection. The rays diverge, spread apart from the tip of the flame, and continue diverging from the mirror upon reflection. These divergent rays appear to originate from a point located behind the mirror. This is why it looks like there's a candle on the other side of the mirror. You perceive the candle flame to be located behind the mirror. This is a virtual image which appears to be in a location where light does not really reach. Mirrors produce only virtual images. So as you're looking at this, as the candle is on the outside of the mirror here, as you look at it, it's producing a virtual image on the other side. Your eye cannot ordinarily tell the difference between an object and its virtual image. The light enters your eye in exactly the same manner as it would if there were an actual image there where you see the image. The image is in the same distance behind you. The mirror as an object is in front of you. The image and object are the same size. So as you stand here, like this, if you look in your mirror in the morning at your house, it looks like there's another version of you standing inside the mirror. The law of reflection holds for curved mirrors. However, the sizes and distances of objects and images are no longer equal. The virtual image formed by a convex mirror, a mirror that curves outward, is smaller and closer to the mirror than the object is. So you see this mirror, it curves like this, meaning it's a convex mirror. So you look smaller, your image is going to be smaller in a convex mirror. When an object is close to a concave mirror, one that curves inward, the virtual image is larger and further away. So this one was closer, this one looks further away and larger. What kind of images do mirrors produce? When light is incident on a rough surface, it is reflected in many directions. Diffuse reflection is the reflection of light from a rough surface, like the one shown here. Each ray obeys the law of reflection, though. The many different angles that the incident light rays encounter at the surface cause reflection in many directions. So as the light comes in, it will hit one of these bumps down here and reflect in different directions. If the differences in elevation in a surface are small, less than about 1/8 the wavelength of the light that falls on it, the surface is considered polished. A surface may be polished for long wavelengths, but not polished for short wavelengths. Whether a surface is a diffuse reflection or a polished reflector depends on the wavelength of the wave that reflects off of it. Visible light that reflects from a sheet of paper is diffusely reflected. Rays of light incident on a paper encounter millions of tiny flat surfaces facing in all different directions. They are reflected in all directions. Diffuse reflection allows us to read the page from any direction or position. We see most of the things around us use diffuse reflection. Almost everything that light hits is diffuse reflection. Very, very few things hit a polished surface. Diffuse reflection allows us to see most things around us. Light is diffusely reflected from paper in many directions, like it says here. Light incident on smooth mirror is only reflected in one dimension. So here we have a very polished as it bounces off and it goes in one direction. And this is called specular reflection. Specular is where it bounces off a smooth surface. What happens when light is incident on a rough surface? Sound energy not reflected is absorbed or transmitted. An echo is reflected sound. More sound energy is reflected from a rigid and smooth surface than from a soft and irregular surface. Sound energy not reflected is absorbed or transmitted. The study of the reflective properties of surfaces is called acoustics. When walls are too reflective, the sound becomes garbled because of the multiple reflections of sound. These are also called reverberations. When the reflective sounds are more absorbent, the sound level is lower, and the hall sounds dull and lifeless. In the design of an auditorium or concert hall, a balance between the reverberations and absorption is desired. The walls of concert halls are often designed with grooves so that sound waves are diffuse. A person in the audience receives a small amount of the reflected sound from many parts of the wall. With grooved walls, sound reflects from many small sections of the wall to the listener, like it's shown here in sample A. With flat walls, an intense reflected sound comes from only one part of the wall. Reflective surfaces are often placed behind and above the stage to direct sound out to an audience. Both sound and light obey the same law of reflection. If a reflector is oriented so that you can see a particular musical instrument, you will hear it also. Sound from the instrument will follow the line of sight to the reflector and then to you. The shiny plates above the orchestra in Davis Symphony Hall in San Francisco reflect both light and sound. What happens to sound energy that is not reflected? When a wave that is traveling at an angle changes its speed upon crossing a boundary between two media, it bends. Let an axle with two wheels roll along a pavement that slopes downward onto a downward sloping mowed lawn. It rolls more slowly on the lawn due to interaction of the wheels with the blades of grass. Rolled at an angle, it will be deflected from its straight line course. The wheel that first meets the lawn slows down first. The axle pivots and the path bends towards the normal. When both wheels reach the grass, it continues in a straight line at reduced speed. If you look at this as it's coming in, it was going in a straight line, but this wheel is going to hit the grass first. When it does, it curves towards the normal, and then when both wheels come in, it will travel that straight line path. When a wave that is traveling at an angle changes its speed upon crossing a boundary between two media, it bends. This is called refraction. Refraction is the bending of a wave as it crosses the boundary between two media at an angle. Water waves travel faster in deep water than in shallow water. The waves react at the boundary where the depth changes. The sample ray is perpendicular to the wavefront it intersects. See, there's our boundary from our picture. This is normal. This is the normal. As it comes in, it then will curve towards the normal as it slows down. Drawing a diagram of water, it is convenient to draw outlines called wavefronts that represent the positions of different crests. At each point along a wavefront, the wave is moving perpendicular to the wavefront. The direction of motion of the wave is represented by the rays that are perpendicular to the wavefronts. Sometimes we analyze waves in terms of wavefronts and at other times in terms of rays. What causes a wave to bend? Sound waves are refracted when parts of the wave from a front travel at different speeds. Sound refraction occurs in uneven winds or when sound is traveling through air or uneven temperatures. On a warm day, the air near the ground may be appreciably warmer than the air above. Sound travels faster in warmer air, so the speed of sound near the ground is increased. The refraction is not abrupt, but gradual. Sound waves tend to bend away from warm ground, making it appear that sound does not carry well. If you look like this, if you have warm air on the bottom and cool air on the top, it's going to curve away so the dog can't hear you. If you have cool air on the bottom and warm on the top, it's going to curve down to the dog. So it's always going to curve to the cooler side. When the layer of air near the ground is cooler than the air above, the speed of sound near the ground is reduced. The higher speed of the wavefronts above cause a bending of the sound towards the earth. Sound can then be heard over considerably large distances. At night, when the air is cooler over the surface of the lake, sound is refracted towards the ground and carries usually well. Suppose you are downwind from a factory whistle, in which case we whistle sounded louder if the wind speed near the ground is more than the wind speed several meters above the ground, or if it is less. You'll hear the whistle better if the wind speed near the ground is less than the wind speed higher up. For this condition, the sound will be refracted towards the ground because it's going slower. What causes sound waves to refract? End of notes, part 1.